In this video, we're going to look at something called equilibrium and eventually get to something else called normal force. And I guess we're going to start with the idea of equilibrium. And if you look at the word, it starts with the idea of equal. Now, hopefully, remember that equal means that things are the same, or almost kind of a state of equality. The way we're going to define that is by using a formula. Now, the first part of this formula is a Greek letter, sigma. And that equals the sum of. So we're going to say that the equilibrium condition occurs when the sum of the forces is equal to 0. That means our forces in the x direction equal 0, and then in the y direction equals 0. So when something's in equilibrium, really two possible scenarios are happening. The object can be at rest, or it could be moving at a constant speed. Or constant velocity. So we kind of look at the at-rest situation first. So if I, just simply take something like a book sitting on a table or a box sitting on a table. I'm just going to make a real quick and easy diagram here. Okay, I have this red box that is just sitting here. And okay, what are the forces that are affecting this? Or what are the things that are actually acting on this? And with a little bit of thought, we say, okay, well, this is here on Earth, and the thing that's pulling it downwards is gravity, or the weight of the object. So we'll say the weight is equal to basically the force of gravity pulling that down. And I guess we want to make sure we understand for sure that weight is a type of force, or the product of a force. So if this is the only force acting on this, according to Newton's second law, which is just simply F equals ma, this should then move downward. Now we know that a box sitting on a tabletop doesn't. It sits there. It is in a state of what we say equilibrium because it's at rest. So we need to have some other force that's acting on this. And with a little bit of thought, we say, okay, well, there must be something pushing against this. And in this case, we would say it's probably something like the force of the table. That force of the table is what we would call the normal force. And we kind of define that. It's a force that acts in a perpendicular direction between two surfaces. So it's not always the most obvious force, but in this case, the weight it pulls down, the normal force pushes back up against it. And that's kind of falling back into Newton's third law. The action forces, gravity pulls the block down against the table pushes up against the block. So that's our first condition of equilibrium, when objects are at rest and the forces that are affecting those. And even though it seems like there's a force pulling down, we also have to have a force that pushes up against that. The second condition is something moving at a constant velocity. So I'm going to clear some room here and put an extra slide. So, oops, stay down here. So this is kind of going back to number 2. Constant velocity. Okay, so something's moving at a constant velocity. About the messiness there. We want to kind of look at this again. So this time I'm going to take make this a surface that's ice. And we're going to put another box on top of this. We'll put a cube of ice on top of it. So I'm going to just select a nice blue color here. might represent what ice would be. There's my ice cube. And this is moving with a constant velocity of about, let's just say 2 meters per second. So it's got a velocity going in this direction equal to 2 meters per second. Now the reason we use ice is for this purpose we're going to say because this is ice on ice, that basically means no friction. So again, thinking back to the forces that are affecting this, we know that there's going to be the weight pulling down against that, and then the opposite force would be our normal force again. So in this case, it's pretty simple to see that as long as this is sliding, according to Newton's first law, an object in motion will stay in motion. If there's no frictional force that's acting here, this should continue to really stay where it is. Let's look at another example, and pretty much the same idea. But this time we're going to take it and we're going to say instead of, I have a brown color here if I can find one, and we're going to draw another line here. So this is wood this time, and my color palette will go away here. Select this and close this up. I'm going to copy and paste my ice cube. Now I have ice on wood. So if I have ice on wood, yes, there is friction. Okay, so it's still moving at constant velocity, constant v, which we're going to say is still 2 meters per second. So again, figuring out the forces that are affecting this, we know again we have the weight pulling it down and the normal force pushing it up, and those are equal and opposite. But because we have friction, and because this is moving in this direction, we know that there's friction moving against that. Now, if this is the only force acting on it, this object must be slowing down. But because it's moving at a constant velocity, we have to have another force. I'm just going to call this the pushing, or pulling, I guess it doesn't matter what. But there's a force pushing this forward to overcome friction. And these two things, my pushing force must equal my frictional force to keep this moving at a constant velocity. So the whole idea for any of these is that the sum of the forces has to equal 0 newtons. So it doesn't mean the thing has to be stationary. It can have motion. It can be moving. Friction can be involved with this. It's just then you have to add some extra force to this. This is like when you're driving in your car and you put the cruise control on. When you put the cruise on, your car continues to move at a constant speed. If there was no friction involved, your car would just keep on moving. But because there is friction involved, whether it's from the tires or from the air resistance, your car continues to burn gas and your engine continues to push your car forward. If you're in space, the reason we can send things very, very far away is because once you get into space, the little atmosphere that there is, really no air particles around. Once you get an object like a satellite or a probe going through a certain speed, it'll continue to move at that speed and really use very little energy because its inertia keeps it moving. So that's our video on equilibrium and normal force.